Hello, everybody, and welcome to the Astro Coffee Hangout, a place where you can go every Thursday at 3 o'clock Eastern Time, grab a cuppa or another favorite beverage that you might have, sit down, relax, and discuss some of the latest developments in the discoveries of the golden era of astronomy. My name is Tony Darnell from deepastronomy.space, and I want to welcome all of you to watching this Hangout live, as well as those of you who will be catching it after we're done. We do these Hangouts on the second and fourth Thursday at 3 o'clock Eastern Time, and they are endorsed by the American Astronomical Society as well as the American Astronautical Society. They pay for the other ones in the other off Thursdays. And while that's true that they endorse and support these organizations do not necessarily endorse any of the opinions expressed in these Hangouts. I always forget to say that, so I'm glad I remembered it this time. Today, we're going to talk about neutrinos. What are they? Why are they so hard to see? And where and how can we see them? Last month, as you may remember, NASA held a live press conference where they announced that for the first time ever, scientists using NASA's Fermi Gamma Ray Space Telescope have found a source of high-energy neutrinos from outside our galaxy. Now, this neutrino traveled 3.7 billion years at nearly the speed of light before being detected on Earth, farther than any neutrino we know the origin of. So our story today started like this. Back in September of 2017, in an event known as IceCube 170922, which sounds suspiciously like a date to me, the IceCube Neutrino Observatory at the South Pole detected signs of a neutrino striking the Antarctic ice with an energy of about 300 trillion electron volts, and we'll talk about what that means later. This will be more than 45 times the energy achievable in the most powerful particle accelerator on Earth. This high energy strongly suggested that the neutrino had to be from beyond our solar system. Now, backtracking the path through IceCube indicated where in the sky the neutrino came from, and automated alerts notified astronomers around the globe to search this region for flares or outbursts that could be associated with the event. Now, our guests today are members of the IceCube team, including Erik Blaufussi from the University of Maryland. We also have Josh Wood from the University of Wisconsin-Madison and Ignacio Taboada from Georgia Tech. And we are going to learn more about the significance of this event from the people who made the observations. Now, I want to invite everyone watching even right now, even those not watching live, to leave your questions and comments in the live chat on YouTube. There's a section for it there. There's also comments for when it's over, as well as our Discord server. And our Discord server, there's a link to that down in the description box, and it's open all the time, and I check it all as much as I possibly can. Also, quick note: my co-host Carol Christian is away on travel this week and couldn't make it today, but she will hopefully be back in time for the next one in 2 weeks. Okay, so let me go ahead and pull up all of my guests here. Here we go. My guest today, and I guess I'll start because I'm doing this in kind of an astronomical Brady Bunch style here. We're all kind of in a Zoom meeting. In the lower left corner, cattywampus to me down there is Erik Blaufussi. He's from the University of Maryland and works on the team. Right next to me is Ignacio Taboada from the Georgia Tech. There he goes. And right below me in the Brady Bunch is Josh Wood from the University of Wisconsin at Madison. Okay. Where should we start, guys? Should we start with what neutrinos are and then what the super neutrino is, or should we maybe talk about IceCube, the observatory, first? What do you guys think?
Or we could certainly start with what a neutrino is.
All right, let's do that, Erik.
Probably a good place to start. So, neutrinos are subatomic particles. They're a neutral cousin of electrons and those type of particles that you see in the standard model of particle physics that we all love in physics. They're created in weak interactions. So these are the interactions that happen, say, predominantly inside the center of the sun, where you have fusion of hydrogen into helium, and in nuclear reactors where you have the fission of heavy elements that break down. You often see neutrinos coming out of these things. That's actually, seeing them coming out of a very high energy neutrino, a high power reactor was the first place they were detected in the 50s. And then later on, they've been detected coming from the sun. And the sun is actually the first extra, outside the Earth source of neutrinos we've seen. And then there was also a burst of neutrinos from a supernova back in 1987 that was also observed. These neutrinos come from, most of them here on Earth are created, in things like nuclear reactors. Let's see, where was it going? The ones we're looking for with an IceCube are much higher energy than you see here on the Earth. They come, as Tony talked about, 300 trillion electron volts, several orders of magnitude higher than anything produced locally by reactors, which are in the millions of electron volts.
Okay, help us understand that a little bit, Erik. What do you
Sure.
mean by these electron volts? I mean, what you say trillions of electron volts. I don't know what to do with that. What context can I have for these? What is an electron volt? And then, what
So
context?
electron volt's just a convenient unit of energy we use to measure these types of things. Your typical, if my understanding is correct, your typical optical photon's around 1 eV, 1 electron volt.
So that would be a
These are
photon that we see with our eyes, things like that.
That's right.
Mm-hmm.
That's right. Most of the ones that are created in nuclear reactors are going to have similar energies to the electrons and gamma rays that are created in these nuclear reactors. That's in the keV up to maybe an MeV type energies. Those in the sun extend up into the tens of million electron volts.
And so
that's from the fusion inside the sun.
So this is just basically a unit of energy that that we use to just describe the kinds of particles. Now, the ones from the neutrinos that we saw from the sun, there was for a while a neutrino problem, right, where we were missing neutrinos, but they discovered that there were actually different kinds of neutrinos.
That's right.
And so then there turned out to not be a problem with that anymore. But what are these of a special? The ones that we're going to talk about today is this new neutrino source from blazars? Are they a special kind of neutrino, different from say what's coming from the sun, or are they just high energy?
Just high energy.
Okay.
So the effect you're talking about with the solar neutrinos was neutrino oscillations. So neutrinos are created in specific types. If they're created along with an electron, they're an electron type neutrino. Now, as they propagate through space, they have their energy is their masses are created by different energy. It's a quantum mechanical effect where you have different mass states that they travel in, and it allows them to change their type as they travel over long distances. So neutrinos created in the center of the sun change their type, and roughly half of them disappear on their way to the Earth, become other flavors that you can't detect with the solar neutrino detectors on the Earth.
Okay. All right. Now, Hans Milling is already asking on the live chat, how do you pinpoint the direction the signal is coming from? I want to get to that, Hans. I really do. But we need to talk first more about the observations, and then we'll talk about how they pinpointed where it was coming from. So let's talk.
I wanted to add something about what a neutrino is.
Okay.
And
yep, go right ahead.
There's one important thing that we missed is that neutrinos are very special in that they interact extremely weakly. They go through pretty much everything without hardly ever stopping. The planet is almost transparent to neutrinos, the same way that light just goes through panes of glass without stopping, the same way neutrinos go through everything without ever stopping. And that is really critical to the way that we detect the neutrinos. We require gigantic instruments to be able to find only a handful of neutrinos.
Now, maybe that's a good point. Maybe this isn't a great analogy here, but it's not too unlike dark matter. I mean, neutrinos really don't want to interact with normal matter all that well. I mean, do they? I mean, they're very difficult to see because they just, like you said, pass through the entire Earth.
It is a great analogy. The interaction of dark matter with matter is about as weak as of neutrinos with matter.
Yeah, we can see neutrinos, but we can't really with dark matter.
We have not seen dark matter.
Yeah.
But we expect dark matter to interact at least as weakly as neutrinos do with matter.
Right. Okay. Josh, did you Josh, did you want to add anything to this little discussion before we move on to the observatory?
I think the only thing that might help is certainly when we talk about neutrinos, we always talk about them as being special in the sense that they're hard for us to detect. But actually neutrinos are made all the time, like we said, in the sun. and they're passing through the Earth all the time. So they're actually relatively common, and they're not that exotic other than the fact that we as human beings have taken so long to figure out how to detect them and observe them.
So it all comes down to us, huh? Okay. Well, let's talk about the detector. How do we detect these things? And I have a lot of graphics that Erik sent. So if you want me, I can put up this IceCube detector diagram if you'd like, and we can talk about the observatory. Do you want to do that now?
Sure, that's probably a great place to start.
Okay. Let me put this up. So I have, oops, I just killed it. There it is. I have the first one you sent me up on the IceCube that basically shows the diagram of what it is. It's up and showing.
Sure. So this is kind of what we see as IceCube. So what we've done is we've built this giant detector down at the South Pole. It is actually directly under the geographic South Pole. When we work there, we travel to the South Pole Station and live and work there while we're constructing and doing maintenance on this detector. It is roughly 1 cubic kilometer of instrumented ice. So we're using the ice as our detection medium. What we're looking for are particles, charged particles created by neutrinos interacting in or near this detector. So a neutrino will come and interact and create a very high energy particle. Typically, for the astronomy aspect we use muons because they point very, very well. And we can talk about the different types we see in another slide or two.
Okay.
But for the detector itself, we've sunk these 86 strings deep down into the ice. Each one is instrumented with 60 of these light detectors, these digital optical modules you see in the lower left corner there. It's not a very great picture of one, but they're essentially a photomultiplier tube, which is a light-sensing piece of electronics with electronics to read it out and control it and send the signals up the wire to the counting house, which is the 2-story building you see sitting in the middle of the detector there in that picture. There are 5,000 of these optical sensors deployed as a giant grid, and we use their known locations, the time of the arrival of the light, to reconstruct the particles we see inside the detector.
Okay, and the ice causes the so a neutrino comes in, interacts with the ice, a very high energy one, interacts with the ice, and some amount of photons are given off somewhere such that these digital optical modules can pick it up.
That's right. And this actually might be a good way to look at the next figure number 3.
Okay. Oh, 3? Okay.
Yes.
I have 3 up now. So
we detect 3 types of neutrinos generally in IceCube. So we're sensitive to all of these. And if there's an electron flavor neutrino arriving at near the detector, it'll interact with, one small fraction of these will interact with a nucleon inside the ice or the rock near our detector and create a high energy muon. This high energy muon can travel then for tens of kilometers at these energies, losing energy all the way, but maintaining the same direction as the original neutrino that created it. Here we can really detect the track of this particle through the detector and use it to reconstruct where the neutrino came from.
So with all of those, and you detect the track via these optical modules, right?
That's right. Okay. So the muon is going faster than the speed of light inside the ice. It's moving near the speed of light in vacuum.
Oh.
And it creates shrink-off radiation as it propagates.
Wait a minute. It goes faster. It goes faster than light in the ice?
In the ice. That's right. It's very relativistic, so it's going near the speed of light in vacuum, which is faster than the speed of light in ice, and gives off this blue glow. Have you ever been near a nuclear...
right. Okay, I get it. Sure. There's speeds of light in different media, and when we talk about the speed of light, generally we mean in a vacuum, but in ice, the speed of light is slower. Got it.
Right. When a particle is going faster than the speed of light in the media, it will give off shrink-off radiation.
And shrink-off radiation, boy, this is going back to my classroom days.
And so we should say it's exactly the same effect as a sonic boom that you get in air. When you move faster than the speed of sound in air, you get a sonic boom. When you move faster than the speed of light in a given medium, you can give off shrink-off radiation.
Oh, good. That's a good way to picture it. Okay. So is shrink-off radiation easy to detect?
It's similar to it's actually identical to what you see in a nuclear reactor, that the water glows blue. because you have all these particles in the nuclear reactor that are going faster than the speed of light in water, and you see the pond glow blue.
Oh, okay, good.
So anything that can detect blue light is able to detect this Cherenkov radiation.
Okay, great. Okay, so I have this. I have this up again. So these are the different kinds of neutrinos that you can detect, and so the direction. And this is getting to your question, Hans, about how you can tell the direction. I have the first slide back up now, where we're looking at all these digital optical modules. So where they appear, where these photons appear in these modules, you track it through the entire grid. Is it a hexagon shape? It looks like it's all in a hexagon.
It's a hexagon shape.
Okay,
that's right.
And then from that you can tell from what direction.
Well, using that slide number 3.
Okay.
It's probably better to tell the thing with the direction.
The 3.
Let's take, for example, the one on the. There are 3 types of neutrinos there. Let's take the one on the left. The one that says CC mu neutrino.
Mm-hmm.
You see that you have little circles that have color, and the color tells you the time when one of the optical sensors has found light. And let's say that red is early and then blue is late. And that right away tells you the direction of the particle that the neutrino created as that particle is going through the detector. And just by the timing and where the optical sensors are, that you can tell the direction of that secondary particle, therefore the neutrino.
Okay. Larry Keys is asking, do all neutrinos detect at the same level? Can you tell which neutrino it is?
You mean the different flavors? Yes.
Yes.
So we have some ability to detect. We can clearly separate the muons because of their long track-like signatures.
Okay.
The other two, the electron type neutrinos and the tau type neutrinos, become much more difficult to disentangle because they both give the same similar type of thing. The electron or the tau that's created don't travel very far. Unlike the muon, they travel tens of centimeters and give off all their light in a big ball of light.
And they lose energy very quickly, the other two.
Very, very quickly in the ice.
All right. Hans Milling is asking, is it necessary to keep the top of the detector free of snow and ice? Do you send people out in the cold with brooms to keep the snow from clogging the detector?
Nope. We naturally let the ice is our friend here. So we use the ice as a shield from a lot of the downgoing cosmic rays that, low energy cosmic rays bombard the surface of the Earth no matter where you are. By building our detector 1.5 kilometers below the surface of the ice, we get some natural shielding from all of that material, and only the very high energy cosmic rays make it down to our detector.
Okay, and so this event, the one that occurred in September of last year, you were able to detect its direction, and then, as I understood what research I've done on this event, you guys there was an alert sent out to people. From where was the neutrino coming, and what was the next? Tell us about that process. You guys detect neutrinos. You go, oh, this is a super high energy one. Get your space telescopes pointed. This was Fermilab, and I assume Chandra might have done it as well. The X-ray telescope that's up there. Tell us about that process a little bit.
I think it would be actually very similar to what you described. There's a computer cluster running at the South Pole, and it's processing all the data more or less real time. And in a matter of, say, 30 seconds from the time that the neutrino passes through the instrument, in a matter of 30 seconds, we know with very high accuracy where that neutrino is pointing. And once a likely astrophysical neutrino, for example, because it has very high energy, has been identified, then there's an alert system that tells that information to all astronomical instruments across the planet, and actually in orbit as well, like you said, like the Fermilab observatory.
Mm-hmm.
And the idea is that the sources of these neutrinos could be transient, they could be bright only briefly. So the faster you can tell where the neutrino is pointing, the more likely it is that you find something in photons that is there to tell you what the neutrino source is.
Now, this observatory isn't like most observatories where you have to apply for time and you get to look at objects. You guys are just on all the time, right? And you're just looking and listening and waiting to find some events that occur. On average, how many events do you guys log and send alerts out for? Any idea?
So when it comes to logging events, we see roughly 2,500 events per second.
Oh, wow. Okay.
But most of these are cosmic ray backgrounds. Yeah.
Oh, they're cosmic rays. I see.
Yeah, that's right.
Okay.
Buried in there are roughly 100,000 neutrinos a year.
So are the cosmic rays your noise? I mean, when we take an image through an optical detector, there's always photon noise and dark noise and things like that are on the detector. Is the cosmic rays kind of your noise?
We also have dark noise because they're photomultiplier tubes.
Oh, right, of course. So you have to subtract that out. But you do need to remove cosmic rays to see your actual signal, right?
That's correct. So, and one of the major ways we can do this is by, having a bias for looking for things that are upgoing or coming from the sides.
Okay.
Things that are downgoing, we if they're low energy, we generally assume they are cosmic ray muons, and we can throw them away.
Okay. Hans is asking, can you detect neutrinos from the entire southern hemisphere, or how narrow is the field of view of the detector? That's good. That's good. Is it a 360 thing, or is it one area of the sky?
We detect events from all directions.
Because as Ignacio said at the beginning, they go through the Earth.
That's right.
That's right.
That's right. So the detector itself is very, it accepts tracks from all directions, even though the predominant of the photomultiplier tubes are all pointed downward in IceCube, but the ice itself has a lot of scattering of light, so we are able to detect tracks in all directions, and we work really hard to understand that we can detect things equally well coming up as coming down. And we have lots of events in all directions to tell us that.
Okay, good. And Larry Keese is asking, the Cherenkov levels tell how much energy the neutrino has. Is it related to that?
It is related to that, okay. Right? So the more energy a neutrino has when it makes its muon, the muon will have more energy. A high energy muon will give off more light as it passes through our detector. And we're able to use that as a scale to estimate the neutrino energy.
All right, so you guys detected this neutrino, and it went out into alert systems, and NASA's Swift Observatory went out and did you guys, how close were you able to get to tell Fermi where to point in the sky?
Sure. So our angular resolution is typically for these type of events about 1 degree. This one is actually a bit better than most, I would say, in terms of once we finally did all the analysis on the event. So the error itself, the error circle is about 1 square degree. So it's a pretty small area for us. Now for astronomers, that's a huge area of space. But for us, that's doing pretty well. Just to set the scale, the cascade events, the shower events, our angular resolution in terms of an opening angle tends to be something on the 10 degrees, that type of scale. The tracks we can do about 1 degree uncertain on the direction.
And a degree, just to kind of give you guys a reference point, if you hold your thumb out at arm's length, that's about 1/2 degree. So twice that length would be the resolution they can get. I don't know what the Fermi spacecraft field of view is, but it's sure smaller than that, or maybe it isn't. I don't know. But the
Fermi is about if you close one eye, what you can see with one eye, that's more or less.
Oh, never mind. It's a lot bigger than that.
Very wide.
So they don't even need that level of precision. They just go point over into that constellation, roughly, and you'll probably get it. So they picked up a blazar, which I guess was a well-known object, high-energy object, very bright. This is when a supermassive black hole on the order of millions to billions of times the mass of the sun ended up is chewing up things all around it, and as material falls in, they accelerate these particles into very high energies, and we're able to see this from very far away. Can you guys? And I didn't get a chance to go into what your area of comfort was in talking about this part of it. I know you guys are from IceCube, but do you guys know much about the event that happened with the galaxy itself and about the blazar? If you don't, that's all right too.
I think all three of us are very qualified to handle any of the questions.
To enter it, what?
I think all three of us are very qualified to answer questions on this subject.
Okay, good. I like I said, I didn't get a chance to go in depth. So tell us about it. What about this galaxy? What did we learn from these neutrinos that came down? Anybody?
Take it.
Ignacio. Hey,
take it, Josh.
Okay, go ahead, Josh. You haven't said much. That's right.
Yeah.
Go ahead.
Well, so for sure, so you have a supermassive black hole at the center of a galaxy. And what happens is the black hole is basically eating stars and material within the galaxy. It's infalling into the black hole, and a chunk of it is falling inside the event horizon. But another chunk of the material has the possibility of escaping, because most things have spin, and there's kind of this nice spin axis. So what will happen is some of the material that's infalling into your black hole is going to escape via two jets that point outwards. And in this case, for this object, we're actually looking straight down the jet itself. And these jets are pretty variable, because you can have larger chunks and smaller chunks falling into the black hole, can create variability in those jets, and can kind of change the properties of what we see coming from them. And so what Fermi was seeing since April is basically this heightened variability in the jet and a heightened flux in gamma rays coming from this object here. And so that would indicate an increase in kind of the acceleration of particles in that region. And then kind of the combination of Fermi seeing that heightened variability in gamma rays and a heightened flux, plus this one very high energy neutrino, what that kind of tells you is it gives you a little bit of insight into the particles behind the gamma rays that were being seen by Fermi, which is that gamma rays can be made both by electrons, which get accelerated, and also protons that get accelerated. But the key difference here is that an electron, if that's the source of the gamma rays that is being seen by Fermi, you wouldn't expect to see a neutrino come from an electron, because it can't produce a neutrino on its own. But if the proton is the source of the gamma rays that are being seen by Fermi, those protons can interact and produce neutrinos at the source, which would describe the neutrino that we see in IceCube. So it kind of gives you this hint that what's happening in the source is actually there's some population of protons that have been accelerated that can create both the gamma rays that we see and the neutrinos that we see. And kind of you get this, combining the two pieces of information, you get this better picture of the object itself. And that's kind of what we generally talk about as multi-messenger astronomy.
Yeah, NASA was very, that's a new term I'm really not that familiar with, but it basically is using different wavelengths to put together a more complete picture of whatever it is you're looking at. And black holes, believe it or not, I mean, we've known about them and theorized about them for centuries. I think Laplace was the first mathematician to actually say something about black holes. But it's only been recently that we've actually proven that we can see them in the ways that we can see something that's absorbing everything that it, or, doesn't emit any radiation at all. These radiation sources that we're talking about all happen outside the event horizon. They all have to do with accelerating particles going into either, whether it's a spinning black hole or not, or whatever it happens to be. We can characterize a little more about what is going on, as Josh said, with these, get a little bit bigger picture of what's going on with supermassive black holes. Were there any surprises here, guys? I mean, were you guys like scratching your heads over anything, or was it just kind of like, oh, this is really cool, we see a little bit more what's going on with a black hole?
Yeah, so for sure, one big surprise is actually this specific object itself. The name of it is TXS 0506 plus 056. And the reason it was kind of surprising is it's actually at a redshift of 0.33, which I believe is 4 billion light years away. Mm-hmm. And that's surprising because they're actually much brighter black holes, much closer to us, that we would have expected to see first. And so that's kind of one of the puzzling things here, is that there has to be something special about this particular AGN, active galactic nucleus, that made it the first one that we detected.
Well, I just thought it was due to the geometry of the situation, right? I mean, the jets were pointing towards Earth, and the detector picked up this neutrino.
So there are actually lots of AGN where the jets are pointing towards us are pointing directly towards us, called blazars. There's a large class of them. I believe kind of on the order of 1,000 objects or so.
I'm glad you specified that. A blazar is still an AGN, an active galactic nuclei. It just happens to have its jets pointed at us.
Yep.
Yeah,
and there are a fair number of them that have been detected. And there's a number of them that are brighter and closer. It's just that for some reason there's something special about this one.
That's interesting. So even though we have brighter, closer blazars, these things pointing right at us, we're not seeing this is the only one we saw a neutrino from. Interesting.
Yep, so far.
There's another thing that I find fascinating, which is actually something that Josh worked on, which is that initially we found this high energy neutrino, and from that you find the gamma rays. And then we looked into the old data from IceCube, the archival data from IceCube at this specific object, and we find another period in which there are neutrinos also being seen from these blazar. However, if you look back at the archival data from Fermi, there are no gamma rays at the same time with these other old neutrinos. So it's hard for me to understand why is it that sometimes you get this period that you have bright in neutrinos and bright in gamma rays, and there are times that is quiet in gamma rays but it's still bright in neutrinos. I also find that fascinating.
Yeah, that is interesting. And you guys, I'm sure, have a handle on all the systematic problems with your detector and observatory, right? So getting this one neutrino wasn't, I mean, as opposed to, say, getting it from somewhere else that Josh would expect, those have all been ruled out, right? There's no systematic problems with the detector.
We did definitely take a lot of that stuff into account. And it's definitely one of the, I think one of the bigger effects is actually the 1,000 known blazars that Fermi has, right? So just, the thing you try to rule out is it's just an accidental coincidence that it happens to land on one of these things in a flaring state. And that's where we really get to the, we have some evidence that it's a little more significant than just random chance that it showed up there.
Okay. Okay, let me get to my Discord buddies. There's some people over there. Dark time. Could neutrinos detectors detect dark matter? Aren't neutrinos pretty much dark matter as they are? We talked about that briefly earlier on. And is there a dark time other than me? I don't know about that part, dark time. But could neutrino detectors detect dark matter? Let's start with that.
So, first of all, I think it's worth pointing out that IceCube has a very rich physics program we do that's beyond just sending out alerts for these astrophysical neutrinos. One of the active things we do is look for evidence of dark matter. I believe that most people now disfavor neutrinos themselves, at least the light neutrinos that we see as their everyday neutrinos, as being a strong candidate for dark matter. They're too light to really to fill the void that we know from cosmology in terms of mass. But one of the things that out there are heavier neutrinos that are sterile. These type of things are all potentials for kind of candidates for dark matter. And one of the things we look for is annihilation of these dark matter particles in, say, the sun or in the center of the Earth or in dwarf galaxies to be, hotspots of neutrinos that would agree with dark matter theories. And so far, we haven't seen any.
Yeah, they also have, and they are similar. I've noticed that there are observatories around the world. I think they might be in Italy and other places where they're using xenon gas, and I don't know much about it, but they're trying to find dark matter particle interactions. If the dark matter particle goes through their gas, among other things, then a flash of light would appear. Those haven't turned up anything yet either. But
that's right. But they're looking for direct evidence of dark matter. So dark matter going through their detector. We're looking for, if you have dark matter accumulating somewhere, it'll self-annihilate and give you regular neutrinos.
Got it. Okay. All right. So that was a good question, Dark Time. And I don't know if there's other Dark Times besides you. I really don't. But you'll always be my Dark Time. How's that? 50 Cent. Is monitoring for a supernova in our galaxy something folks watch for? My reading suggests a neutrino event will lead gamma rays, etc., by a couple of hours. Is this true? I can read it again.
Yes,
I read that kind of fast.
It is correct. Depends on the type of supernova, but there's a lead time that the neutrinos have with respect to the light. And any neutrino detector in the world worth its salt, and there are quite a few, will have a system that is monitoring the galaxy all the time. And in the case of IceCube, because we can see neutrinos all the time, and we're operating the detector with 99.9% uptime, then we're really well placed to say there has been a supernova in the galaxy. And in that case, we would send another alert also really fast, so that other astronomers are on the lookout for that supernova.
Okay, can I show that little animation you sent me, Erik? Sure. That I'm going to go ahead and cue it up, and it's playing as you talk. I've just got it looping. You explain this animation to us a little bit? It goes back to how the observatory works, I believe.
So this is actually a movie created by our event viewer of the Alert Neutrino event, right? So what you're seeing there is the arrow represents our best fit, what we think the track of the muon that was created by this neutrino took through our detector. And the colors represent the times, as Ignacio pointed out earlier. Red is the earlier times.
Oh, yeah.
And darker blues are the later times. And you can kind of see that as it progresses through the detector, you're lighting up. First of all, the amount of light being deposited is kind of given by the size of the hits themselves. So you see we're getting a lot of light here, and we're able to tie all this together and use all this information to really tie down the track and tell us exactly where it came from.
Yeah, this is a good illustration of the colors. I'm going to go ahead and just put back that third slide we had where the colors were there,
sure.
Because it really helps. I should have shown this first. So these colors, these red colors, are earlier, like in the CC muon neutrino track, and then the track sort of goes from the lower left to the upper right.
That's right.
In that graph. So that's really cool. That's really a neat thing. So do you want to show any of these other graphs very briefly, Erik, or do you just want to, we pretty much covered what you guys saw? Is there any of these other graphs might I put up?
That's a good question.
Yeah.
So we have ones that should kind of show how well it's correlated in space. I don't know if you want to talk about that. That's I guess it would be number 7.
Yeah, I do actually. So let me get all my other stuff out. Okay, I've got that up. That's a good one. So this is showing where in the sky.
That's right. That's right. The detections were made.
This event occurred. I like that. Yeah.
Right. So somewhere in the middle there is a dot. So you have a zoomed in picture in the upper right corner. Here the kind of greenish yellow line is the uncertainty position from the MAGIC Air Shrenkoff telescope. I don't know if you've ever had anyone talk about an Air Shrenkoff telescope, but they measure very, very high energy gamma rays in the hundreds of billion electron volts to into the trillions of electron volt gamma ray energies coming from these sources.
No, we haven't talked about that too much. Now those
so
need to be in
the atmosphere itself as a detector for the particles. So they see these very high energy gamma rays come in and strike the atmosphere and create this giant cascade that they measure on the ground on dark moonless nights.
So they're monitoring the sky for these particles as
they're
they come.
Pointed instruments, and they so they responded based on our alert and pointed their Air Shrenkoff telescope in La Palma at this location.
So Shrenkoff radiation can be detected by looking at its interaction with our atmosphere.
That's right.
These particles can come in from our atmosphere.
That's right. So this gamma ray has such energy that it accelerated a group of particles in the atmosphere, and they gave off Shrenkoff radiation, and they were able to detect it there on the ground.
Okay, well that's really good. And one thing, well that reminds me. I guess I meant to ask earlier myself. I was thinking about this high energy neutrino, and that we know neutrinos are weakly interacting with normal matter, but they're such high energy. This one in particular, that's not affected by things like the atmosphere or anything like that, right? The fact that it's high energy doesn't matter so much as the fact that it's a neutrino, right? Because high energy gamma rays and cosmic rays, they don't get through the atmosphere.
They would not get through the Earth, or charged cosmic rays would not get through the Earth to this point. Now, if you go to very high energy neutrinos,
like this one,
a little bit higher perhaps in the PeV energy range, they will not make it actually through the heart of the Earth. So you will never see a very, very, very high energy neutrino coming up. They're guaranteed to interact somewhere in the Earth before they reach our detector at high enough energies.
Okay. And Ascanio Vitale is commenting Gran Sasso in Italy. That's right. That's the one I was thinking of. That's the observatory. Launchpad Astronomy. Hi, Christian. Hypothetical causes, an event inside a jet, perhaps? He's asking about this event. Is there any hypothetical causes for?
There's definitely, one of the things that IceCube was kind of built for. So we've known about these very high energy cosmic rays that bombard our atmosphere for over a century now. They were detected in the early 1900s. Victor Hess went up in a balloon with a radiometer and saw this increase of these particles coming from the atmosphere. The lower energy ones, I think people generally understand coming from the from the solar system, from the sun itself. Up through middle energies, maybe supernova are the good explanation, but the highest energy ones are still a mystery where they're coming from. Okay. When you have these particle accelerators, you'll have these protons being accelerated to very high energies. They're going to be in some dense environment, in some accelerator media. They're going to create neutrinos. Some fraction of them are going to interact, create a neutrino. And so we're trying to use these neutrinos as kind of the smoking gun to say that's a potential source of the highest energy cosmic rays.
Okay, good. Dark Tom is asking, how many neutrinos have been detected? Hundreds or millions or billions? Well, as we mentioned earlier, you're seeing about 2,500 a second, right?
No, not neutrinos. Those are cosmic ray muons. So 2,500 cosmic ray muons and things from cosmic rays per second. We see about 100,000 neutrinos per year. Now, most of those aren't astrophysical. Most neutrinos we see are created in our atmosphere. Those same cosmic rays that interact in our atmosphere, one of the things they're going to be creating are neutrinos. And those become a background that we have a very hard time differentiating. And here we really need to use the energy of the event.
Okay.
Astrophysical neutrinos have much higher energy. And our estimates now, we're seeing 10s to 50 astrophysical neutrinos per year. Some are going to be high enough energy that we're going to be able to clearly state that this is an astrophysical neutrino on its own, and others require, some understanding and analysis of all the events and looking at their spectrum. So we send about 8 alerts per year with the system. If that sets the scale for astrophysical neutrinos, we can alert on.
Okay. Do you see a need then? Do you guys pretty confident you're seeing them all? Is there a need for another observatory, or does IceCube pretty much fit the bill? Like, would we benefit from doing this, I don't know, in the Arctic Circle or something? Having another...
I can certainly try to take this. So, we're definitely starved for data, right? We're talking about, we saw 1 neutrino for this alert, and then we saw maybe 12 or so at an earlier flare that really made up these 2 papers. And to really understand the internals, and we need to be able to generate spectra. And doing that with 1 or just 10 events is very, very difficult, and a lot of uncertainties come into your measurements. To really understand what's happening inside, we need more data. And I think that it's a great start what we're doing with IceCube, but I think that there's definitely room for bigger and more detectors.
Well, that's what I was going to ask. Is it enough to just make IceCube bigger than what it is now, or do you need others placed somewhere else, or maybe around Antarctica or even other places on Earth?
So there are others being built right now. There's a smaller neutrino detector operating in the Mediterranean, deep in the ocean, called Antares, and they're working on its bigger brother right now called CAM3net that'll do a lot of the similar things to IceCube. They're looking to do, but they're of the similar size of IceCube, so they're going to have similar event rates to IceCube. Now, we'd love to make IceCube bigger and be able to send out more alerts and detect more neutrinos.
How do you make a spectra of these? I'm trying to imagine that. You said you would love to make spectra of these. How do you do that?
So we can, on a per event basis, get an estimate of what the neutrino energy was, and then be able to say, okay, this fits this source hypothesis that says the neutrino should be coming out with this spectrum.
I don't get it. You have a neutrino of a certain energy. You then just say, well, if it's got this energy, then here's its spectrum.
Well,
but you need more than one for sure.
Yeah. So an easy way to do it, which isn't quite what we do in the full analysis, but it's kind of similar, is you can say you can make energy bins. You can have a bin for lower energy events, a bin for medium energy events, and a bin for high energy events.
Sounds like the double slit experiment.
And you can but you can count the numbers of events in each bin and basically tell if you have a falling spectrum, which would be you would have fewer high energy events than low energy.
Of course, I get it now.
Right.
So a neutrino is kind of like a photon of a certain energy. It's going to fall in a certain part of the spectrum. Okay, I get it now. That's why one neutrino isn't going to get you much. You need many neutrinos that you can build up a scatter plot of that, and that scatter plot is the spectrum, and I get it now. Okay.
Right. Yeah. So with this one high energy event, you can imagine if we built another experiment exactly like IceCube, you would observe two high energy events because you have two experiments of the same size, and that helps you a little bit. But ideally, we'd want 10 experiments.
Sure.
You'd want a factor of 10 more to really be able to measure a spectra and get more information about the sources.
Is this place manned all year long? I mean, is somebody there all the time, even in winter?
Absolutely.
Okay.
So roughly 50 people stay at the South Pole station over the winter.
Uh-huh.
They close up shop, and so they work. The main working time down there is the austral summer, which is Christmas time for us.
Mm-hmm. Yeah, it's coming up, isn't it?
Mid-October is typically when the station opens, and then closes down in mid-February. And the people that are there when the last plane leaves stay until October. Okay. And we have 2 dedicated winter rovers that are down there making sure our detector's running all the time.
Okay, I'm going to ask this.
A critical component to make sure we have that 99% uptime.
Good. Well, I'm going to ask this because I'm a software engineer and I worked on data pipelines for different projects, and this kind of thing interests me. What's the data like from this observatory? Is that, with most observatories, you end up with images, and you take all kinds of images. You can get petabytes of data. That's image data. What kind of data comes out of the observatory? Is it an image? Is it they're photomultiplier tubes? So are they what are they? What do you get out of the observatory?
So we have photomultiplier tubes. We have roughly just over 5,000 of them down in the ice. Each one has a time sampling. So you get a waveform. What the photomultiplier saw as a function of time. They self-trigger. They're an independent data collection unit themselves.
It's like a series of numbers that show a bright little thing, and then it trails off.
Yep.
Okay.
And that gets piped to the surface where they're grouped together into collections and you have a trigger that says, okay, in this 5 microsecond window, I saw 10 DOMs with hits. Therefore, something happened. Let's save the data.
Oh, good.
From there, you send it off. You deconvolve the waveforms and try to find the arrival time of photons and hitting the entrance to the photomultiplier tube. From there, then you try to reconstruct tracks, and we do this all in real time.
Yeah. So the data is basically, so we showed that picture earlier of that one track-like event going through the detector.
The animation.
So the animation. Yep. And so that's basically a snapshot of the detector for, like Erik said, 5 microseconds or so. And so the data is basically just a stream of events like that, where you take these snapshots of what the individual PMTs are doing within a fixed window. And then you use those snapshots to reconstruct the individual events.
I don't get the sense that this is a lot of data as far as bytes are concerned. Is that right? Is it not like an image would be?
The raw data is about a terabyte per day.
Oh, it is a lot of data. Okay. That's
so most of it gets stored on tape and on disk at Pole. We send roughly 100 gigabytes per day back over a TDRS satellite system.
Oh, really? I was going to ask you about that next. So you go through TDRS then. That's the space. That's NASA's space internet. That's what they use to communicate.
Right. So we have a space allocation on that from the National Science Foundation. They send us. We get our data up here in the north every day. We also have for the real-time alerts, TDRS is too slow. It takes roughly a day to get the data through it. We have an Iridium modem bank where we use Iridium modems as basically an old dial-up system where we have a always-on data connection to the South Pole where we can send these alerts.
Holy moly, that must be expensive.
So we send basically text message from the South Pole over this Iridium link to our servers in the north, and we then issue the alerts.
Cool. That's really, so there has,
we can get it all done from end to end in under a minute.
so the alert part of it needs to happen on site to happen quickly.
That's right.
And then those alerts go out via these Iridium communications networks, which are a lot slower actually than what you're normally used to with internet connections. Well, that's interesting. Okay, and I didn't know you used TDRS for this either. That's really interesting as well. Andrew Planet. Oh, you're talking to Launchpad Astronomy. Okay, so let me see here. Hang on, I gotta scroll a little bit. Where'd my cursor go? There it is. Okay. Adam Synergy is asking, are we close to making ultra-high energy neutrino detections alongside gravitational wave detections? That's a good question. Talk about your multi-wavelength astronomy. Are you able to coordinate anything with LIGO yet, or?
Yep. So we actually already are. We work jointly with them, with some members from their collaboration, and there is an analysis that we've designed that can jointly detect neutrino emission coincident with gravitational waves. And the hope is we'll get one, but we haven't found one yet.
That would be cool, wouldn't it? I mean,
yeah.
You get a gravitational event and you see all these neutrinos hitting your detector. I guess that would be first, wouldn't it? You would see it before LIGO would. I don't know.
I'm not sure about that because it should be the gravitational.
They're pretty close to the same speed, aren't they? That's right. Gravitational waves aren't bound, I think, by this speed of light business.
If you're thinking about neutron star mergers, the neutrinos probably would come a little bit later, but almost
not much. Yeah.
The difference would be really small. The gravitational waves would occur first, but the difference would be really small. But who knows, because we have not seen them together.
Yeah. Well, here's hoping. Talk about the golden age, folks. That's amazing. Let's see. What is the... Oh, here's a good question. Asciano Vitale is asking, what's the effect of redshifting on neutrinos? Are they redshifted like normal photons?
They are exactly the same way as light. The effect will be identical. We're talking about neutrinos that have extremely high energies to begin with anyway, but the overall effect is identical.
So you're talking about a neutrino that was in the TeV, the tera electron volts, right? And if it came from a redshift of, what did we say, 3 or 0.3? I forgot what you said. 0.3. Then that would probably have been redshifted into what we saw, but it was probably higher energy when it left, right?
I mean, the typical thing is that you do 1 plus the redshift is the original energy. So this will be the original neutrino at the source would have been, 1.3 times higher energy. Right?
Oh, that's a good rule of thumb.
I'm getting that right now.
Oh, good. That's a good rule of thumb. I didn't know that. So, let's see. So they are affected by redshift, just like everything else. Then they're not special in that way. So that's good. What was the? Oh, I know what I wanted to talk about before we go. We're running out a little bit of time, but I wanted to ask you guys. We talked about this very briefly before the Hangout started. One of the things that I've noticed in astronomy these days is that you guys came from the particle physics area of science, of physics. And I've noticed that with the study of various projects that are out there, and I use the example of the Dark Energy Survey where I worked for a couple of years, they had a lot of, first of all, the project was funded by the Department of Energy, and Fermilab had a big role there, and almost everybody at Fermilab in Illinois was a particle physicist person, although they were hiring more astronomers in their building, which I found was an interesting trend. So you guys are also working, although as Ignacio pointed out, it's not the same connection, but can you talk a little bit about how particle physics and astronomy are starting to become a little more relevant to each other?
I think there are maybe a couple threads there. One is that traditionally, and that has changed a lot in the past couple of decades, but traditionally, particle physics was at the forefront of computing and large data management. And that area of techniques was probably a little bit more advanced in particle physics than it was in in astronomy. So when astronomers began a couple decades ago to get into large data sets and data management, particle physicists were able to help in that part. And now, of course, they don't need any help. Now, as you have astronomers that are, amazingly good with doing that, they don't need the particle physicists for that respect.
So the infrastructure for doing a lot of this astronomy now started in particle physics world at accelerators.
The large handling of data is something that particle physicists have done since the 70s, and many other areas of science, including astronomy, are doing that nowadays. I think that's one contribution. I think the other is that neutrinos are initially a topic of particle physics itself. So it's very natural that if you're building a neutrino detector, you end up with a bunch of particle physicists working in that instrument.
Yeah, but I think there's also a bit of history here too, which is that before we could build our own accelerators, we used the universe, right? Kind of the original particle physics people were looking at cosmic rays and things like that because the accelerators were free. You don't have to build one. And it turned out we got good at building them for a little while, and we can build them up to a certain energy, but the LHC is kind of topping out. I believe it's 7 TeV is the beamline now, or 10 TeV, something like that. And if you're a particle physicist and you want to go even higher, you basically have to do astronomy because we struggle to build things a higher energy than that here on Earth.
That's amazing. So yeah, if you want to see these super high energy particles, you really kind of need help from the universe. Although, I mean, the LHC is amazing, and from what I've heard, it's I think they have to like let the country know, Switzerland know they're about to turn it on so that they can be ready for it. But one more question from Dark Time, and it's a good one. I like this question. Are neutrinos polarized? What properties of them can you detect other than their energy? That's a really good question. Are neutrinos polarized?
Yes, but we do not have a way of detecting that. And neutrinos have a spin, and in principle, well, that's actually a complicated question. Neutrinos have a spin, and we can, in principle, detect the spin of the neutrino. In practice, an instrument like IceCube is not able to do that. The detection of the spin of the neutrino in itself is interesting for particle physics reasons, because it's related to the distinction between neutrinos and antineutrinos, or going down the really deep hole of particle physics really fast here.
Well, it's a really good question though, and I'm going to leave it one more quick question because this one's quick. I think we can answer it quickly. Larry Keys is asking: so the flight path of the neutrino is being constructed locally at the detectors, right? You're doing all of that work on the computers in the South Pole.
At the South Pole, correct.
Right, and then you're sending out the alerts.
That's right. We reconstruct the muon that was created by the neutrino.
Okay.
And we know from particle physics how well those two these energies are strongly correlated in direction. Okay. But we're able to say we reconstruct the muon direction. We know it's the same as the neutrino at this energy. Okay,
great guys. All right, well, we're out of time. I'm going to go ahead and stop it there. My guests today were Dr. Erik Blaufussi from the University of Maryland, Josh Wood from the University of Wisconsin-Madison, and Ignacio Taboada from Georgia Tech. All of these guys work on IceCube, which is a South Pole observatory which had a detection recently of a super high energy neutrino, which is linked to a supermassive black hole, blazar active galactic nuclei, all kind of fun stuff embedded in there. And we're getting better at this. We're getting better at detecting neutrinos, and we've got a bright future, it looks like, for these super high energy particles. So I want to thank my guests for taking the time out to explain a lot of this to us and to bring it to you. You guys had great questions. It's not over, folks. If you guys want to watch this, if you're watching this after we close, leave us questions in the comments. I'm also on Discord, and if I can't answer your question, I will maybe email these guys and have them maybe answer the question for you if they have the time. But so it's not over, so please take part. I want to thank everybody for watching these hangouts. Next week we have our Future in Space hangout with Harley, and we're going to be talking about the gateway to space. from NASA. And then following that, the next Astro Coffee Hangout. Carol, remember I promised you Dr. Adam Frank from the University of Rochester. He's the guy who wrote a paper about is climate change a possible great filter. So we're going to be talking about that in 2 weeks. So, and Carol should be back for that. So on behalf of my guests, on behalf of Carol Christian, and you guys who are awesome space fans, thank you all so much for watching. And as always, keep looking up.